Oh, hey, Miss T.
Oh, hey, Mr. A.
Oh, wow, you seem really positive today.
Well, yeah, we're about to do some math, and everything about math is positive.
Everything, including negative exponents and reciprocals.
Well, yeah, we're just gonna take those negatives and turn them into positives anyways.
Sick.
You mean sick?
Well, let's fill in this table. We're going to write all of these exponents as repeated multiplications or divisions. But to kick this off, I'm going to say that x to the 1 is 1 times x. And I'm going to say that x squared is 1 times x times x. And it's kind of necessary that I keep that 1 there. Take a moment. Keep filling things up this way to x cubed, x4, x to the 5th, and then we'll see what happens here. If you're really daring, you can see what happens if we go the other way, but we're not quite there yet. Well, assuming that you've taken that moment, x cubed can be written as 1 times x times x times x. X to the 4 is 1 times x times x times x times x. And x to the 5 is 1 times x times x times x times x times x. Worth asking is, of course, this question, as we go from one row to the next row up, what operation do we perform? So as we go from this row to this row, what do we do? As we go from this row to this row, what do we do? Some people might be inclined to say that we just add an x, right? There's 3x's here, there's 4x's here, so we add an x. We're not actually adding x, we're not saying plus x to get to the next row. We are multiplying by x. So to go from one row to the one above it, we must multiply by x. So then that begs the question, what happens as we go down the rows? As we go from x to the 5 up here to x to the 4 right beneath it, how do we do that? As we go from x cubed to x squared, how do we do that? And similarly, we're not taking away an x, we're not subtracting an x. To go from here to here, we actually have to divide by x. That x looks weird. Whoa. All right. That is what allows us to fill in the rest of this table. So to go up, we're going to multiply. To go down, we divide. That kind of gives us reason for believing that x to the power of 0 is equal to 1. We divide by x, this x disappears, and that's all we've got left. But we can go further down. Again, every time we go down a row, we are dividing by x. So x to the negative 1 is 1 divided by x. And if we go further down, x to the negative 2 is 1 divided by x, the row above it, divided by x. And continuing, x to the negative 3 is the row above it, but divided by x. X to the negative 4 is the row above it, but divided by x. And x to the negative 5 is the row above it, but divide that by x. So how do we work with negative exponents? How could we rephrase x to the negative n as something with a positive exponent? Well, it looks like on top of a fraction we'd have a 1. We'd be dividing 1 by something. What would we be dividing 1 by? Well, if it's x to the negative 3, you're dividing by x 3 times. Or if it's x to the negative 4, you've got x there 4 times. So similarly, if it's x to the negative n, you're dividing by x n times. So we could justifiably conjecture that this is the case. This is the equivalency between a positive and a negative exponent. And good news, it's true.
What? Cool.
Good news, it's true.
So, taking a look at this, when we look at any sort of power, or a power with a negative exponent, what we're going to do is we're going to change that negative exponent into a positive exponent. We're going to change the sign. But in order to do that, we also have to take the reciprocal of the base. So we're essentially flipping that fraction. So let's take a look at a couple of examples. So this first example here, first of all, let's just keep in mind that we're not evaluating these answers. We're just trying to rewrite these with positive exponents. That's all that the instructions state to do, so that's all we shall do. So what I want to do is take this negative 8 as an exponent and somehow turn it positive. Well, I know that I will have to take the reciprocal of my base. My base right here is 7, or 7 over 1. And to take the reciprocal of that, well, that's just 1 over 7. And that turns my negative exponent to a positive exponent, to a positive 8. Now, very often, you will see that we don't write 1 to the power of 8 over 7 to the power of 8, although we can based on our exponent laws. The only reason we don't do that is because 1 to the power of 8 is just 1. And so writing 1 to the power of anything, doesn't really change anything. So you'll notice that similarly here in this kind of conjecture that Mr. A wrote, you notice that this 1 isn't to the power of n. It very well could have been, but it doesn't actually change anything. So looking here, we took the reciprocal of our base to make it 1 over 7. These exponents, or this exponent, was distributed to both my numerator and my denominator. And then, we never really write 1 to the power of 8, so we just write it as 1 over 7 to the power of 8. And my exponent is now positive. I am a happy camper. I would like you to try this next one, as well as the one after it on your own if you're feeling bold. And if you're not, that's okay. Maybe you'll feel more bold after this example. This example we're taking in, we have a negative exponent to the power of negative 9. We have to take our base, which is 1 over 4, and take its reciprocal. The reciprocal of 1 over 4 is 4 over 1. And 4 over 1, we're not going to write 4 over 1, we're just going to indicate that as 4. And my exponent, now that I've taken the reciprocal of the base, becomes positive, and so I get 4 to the power of 9. Let's keep in mind that you could very well write it as such, then distribute that exponent to both the numerator and the denominator, 4 to the power of 9 over 1 to the power of 9. Then realized, hey, we never write 1 to the power of something. So just go 4 to the power of 9 over 1, and then said, hey, that's kind of we don't really need to write over 1. Dividing by 1 doesn't change anything, and indicate their final answer is 4 to the power of 9. The steps are kind of the same. You're just zooming through those because our denominator was 1 to begin with. This last example, now we have a fraction in which the numerator and the denominator are both not 1, but we still deal with it in the same way, right? We have this negative exponent. To make that negative exponent positive, we take the reciprocal of the base being 9/5. The reciprocal will be 5/9. And my exponent goes from negative 3 to positive 3. Now that 3 as an exponent by my exponent rules can be distributed to both the numerator and the denominator. So I get 5 to the power of 3 divided by 9 to the power of 3. And because neither of those are 1s, that's all we're going to do.
Now that we can express negative exponents positively, we can also evaluate expressions that have negative exponents. So what evaluate is to find the value of either as a decimal representation or as a fraction-y fraction. When we look at something like this, 4 to the power of negative 2, we can rewrite it with a positive exponent. We can say that we're dealing with 1/4 to the power of positive 2. And then apply that to both the top and bottom. 1 squared over 4 squared. And then evaluating each, so making sure there's no exponents in our final answer. 1 squared is 1, and 4 squared is 16. So 4 to the power of negative 2 is 1 over 16. See if you can tackle the other 3 in this set of examples. Give them a try, give them a go, see what happens. And I will move to the next one. 2 to the power of negative 3 is the same thing as taking the reciprocal of the base to the power of positive 3, which is 1 cubed over 2 cubed. 1 cubed is 1, 2 cubed is 8. 1/3 to the power of negative 4. Again, we flip over the base, we take its reciprocal, and that's what allows us to change the sign of the exponent. Applying that exponent to both top and bottom gives us 3 to the 4 over 1 to the 4. 3 to the 4 is 81. 1 to the 4 is 1. It's really just 81. And as Ms. T was saying earlier, because we know that 1 to the power of anything is 1, really, you could even write this step as just 3 to the 4. So just note that. But of course, sometimes the reciprocals and even their originals won't involve 1s at all. Like this! But we still operate the same way. So we're going to take the reciprocal of that base, and by taking the reciprocal of the base, we can change the sign of the exponent. By the power of a quotient law, we can say that we're taking 2 to the power of 5 and dividing it by 3 to the power of 5, and then evaluating each of those. 2 to the power of 5 is 2 times 2 times 2 times 2 times 2, which these days is 32. And 3 to the 5 is like 3 times 3 to the 4, so 3 times 81 gives me 243. We don't have to worry about being able to simplify this fraction. If the original couldn't be simplified any further, well, then neither can that. They won't have anything in common because these didn't have anything in common. And that's all I have to say about that.
Ooh, I have some stuff to say. We've looked at what happens when we have negative whole number exponents, but it's just as possible to have negative fractional exponents.
Whoa.
And we've already dealt with fractional exponents in the previous lesson, and dealing with negative fractional exponents is really just the same as dealing with negative exponents and dealing with fractional exponents. The steps are going to be the same. What we do recommend is that we first account for the negative exponent. So we're going to take the reciprocal of the base first to turn that fractional exponent positive, and then kind of continue working on it in the same way we would in previous lessons. So let's take a look here. So 64 to the power of negative 2/3. We are going to start by getting rid of that negative exponent. To do that, we will take the reciprocal of the base. So 64 over 1 becomes 1 over 64. And that changes our exponent to negative 2/3 to positive 2/3. And now that we have a positive fractional exponent, this looks a lot like our previous lesson. Just like the quotient law in exponents, our exponent can be applied to both the numerator and the denominator. 1 to the power of 2/3 over 64 to the power of 2/3. 1 to the power of anything is really just 1. So regardless if that is a fraction or a whole number, it's really not going to change anything, so we can just indicate that numerator as 1. Now 64 to the power of 2/3, well, you know what? That would be a lot easier to evaluate if I indicated that as a radical rather than an exponent. So I'm going to go ahead and do that. Remember that my denominator represents the index of my radical, And the numerator represents the power or the exponent of my radicand. And we can go ahead and do 64 squared first.
Ugh.
But to be honest, that's a big number, and that's a little bit terrifying. Because I have to do that all calculator free. So what I'm going to do is I'm going to take the cube root of 64 first. That'll be a little bit easier. And by a little bit, I mean a lot. The cube root of 64, well, that's just 4. I still have that squared up in there. So I still have to deal with that. But I know what 4 squared is. It's a fun game. But it's also 16. So my final answer will be 1/16. All right, this last example, I'd like you to try and do it on your own. Because you've got skills and now's the time to use them. No, here we are together. So notice that we have 25/9 to the power of -3/2. So we're going to deal with that negative in my exponent first. And to do that, I'm going to take the reciprocal of my base, so that turns into 9/25. And my exponent turns into 3/2. One really crucial thing is I am taking the reciprocal of my base. I am not taking the reciprocal of my exponent. That is like a huge math no-no. So all my exponent is doing is going from negative to positive. It is not going to 2/3. I am not taking the reciprocal of that.
We're emphasizing that because that is an error that we frequently see.
Oh, it is so common, but so very wrong. We're only taking the reciprocal of our base. The exponent only goes from negative to positive. We are not flipping it as well. All right. If that was not clear, hopefully, we will see that down the road. It may be an example of what not to do. Man, I got a little worked up after that.
Yeah, how you feeling?
Honestly, pretty good, because I know that now I'm not going to take the reciprocal of my fractional exponent. That would be wrong.
Plus, everything about math is positive.
Oh, you betcha. All right. Whew. So now what we could do is, by the quotient law, is distribute that exponent to both the numerator and the positive. I was going to say positive.
The posinator?
Yeah, so the numerator and the denominator. So I have 9 to the power of 3/2 over 25 to the power of 3/2. And again, I can't really evaluate that without converting it to a radical, so I'm going to go ahead and do that. My denominator becomes the index, so I have the square root of 9 to the power of 3 over the square root of 25 to the power of 3. I go ahead and do my radical first, and so the square root of 9 is 3, so I end up with 3 cubed. And the square root of 25 is 5, so I have 5 cubed. Last but not least, I have to get rid of them cubes, though. 3 cubed, 3 times 3 is 9, times 3 is 27. And my denominator of 5 times 5 is 25, times 5 is 125. And just like what Mr. A said, we don't have to double check here to see, can this be reduced? Because just like in the beginning, that was not reducible. My final answer is also not going to be reducible because all of my factors of my numerator have nothing in common with the factors of my denominator. So I do not have to worry about that. Alright, so we've got some textbook practice, and we've also got a quiz coming up. So now is a great time to review all of the stuff we've learned so far, and ask any questions that maybe you didn't ask yet. That's it.
Yeah, sorry, I'll chime in. Bye.
Bye, have a great day, we miss you!